Drop the ball on that one. That's okay. It's okay. I like this. It is, but where are they? So you know how to spell it, right? I just feel like keep it on there. I don't ever use this, so. So pretty good. Any of you guys use PowerPoint? You know how to go to like full screen or whatever?
Yeah.
On slideshow. Bottom right of slideshow. Bottom right. It's the one that touches. Okay. All right, everybody. Well, welcome. Before we start, we're gonna give the math in a play. Y'all probably all got an email from me, so consider doing that because it's a lot of fun. Help out your fellow students and all that. And there will be pizza there, and then the people that actually eat. We don't serve it to the undergraduates, so you all do. But anyway, so it is my pleasure to introduce to you Andy Vaccaro, who is going to talk to us about Anthony Carl, I'm sorry, who's going to do an analysis of the n-body problem.
All right, so thank you all for coming. My name is Anthony Vaccaro. And over the summer, I did research for Math 4820 on the n-body problem. I'm just gonna go through it, give a basic introduction, some background, my results from the research, and the future of the problem, and how I got the opportunity to do that. So an introduction. What is the n-body problem? The n-body problem is pretty much predicting of individual celestial objects in space and their motion for n number of bodies. So wherever you want to end it. And their applied forces. So a basic foundation of the problem, we can start by looking at Newton's law of universal gravitational equation, which is right up there, F equals G of 1 and 2 over R squared. You probably already know that. And after applying Newton's second and third law of motion to get a vector variable where I does not equal J, you get the following equation of MI AI equals the sum of J1 to N of energy JI. So why do we want to solve the n-body problem? Motivation for solving the n-body problem started once the two-body problem was solved by Isaac Newton back in the 1600s for when n equals 2. And solving the problem would give us the desired answer we want for movement of celestial objects in space that we can observe, whether it's just them as a group or just one individual body. Me personally, I was really interested in celestial mechanics, and astrophysicist Henry Poincaré said in the 1890s that the problem, a general analytical solution was not solvable. So that made me want to give it a go. Background: how did the n-body problem come to be? Isaac Newton first asked the question in 1867 in one of his philosophy essays, Philosophy Naturalis Principia Mathematica. And the reason they wanted to know that the solution to the n-body problem way back in the day was for travel. So you could look up at the stars and see where the stars are to know where you are, where you need to go at tea time. How's the problem solved and changed over time? Well, as people found out that there wasn't really any analytical solution and computers being invented, coding started to come about, we started using algorithms and simulations. And there's loads and loads of different tree algorithms you can use. I have some listed right over here: the tree, the burdens on a tree, fast multiple method, parallel multiple tree. You can use any one of them. As I was digging into research and playing around with the analytical solutions, I found multiple. You can probably just Google it, honestly, n-body problem, coded simulation. There's plenty of them out there for like beginner, intermediate ones you can find in Python. Unfortunately, the ones that are on a big, massive scale that they would use for finding new groundbreaking research was done on super quantum computers, which I did not have access to.
Hey, Anthony.
So stable versus unstable solutions. So there are very specific solutions for very specific examples, such as some pictures right here of when a body is it's stable, it moves around without chaos, as they say it. And I'm just gonna have some videos, examples of different ones. So this is an example of a chaotic three-body problem. It's unstable, and inevitably a third body will get flung out of orbit, and it'll become a stable two-body problem. And here are some periodic ones. Here are some stable versions of the three-body problems. Orbit. And a good way to visualize this is you see it in the next video that I have up shortly. It's called the sphere shape, even though it's not a sphere, it's a triangle between with each mass body as one of the points of this triangle. And you can see as it moves, you won't really care about the orientation of the triangle or the size of the triangle, but mainly the lengths of each side and the angles at each tip in relation to one another.
Hey, Anthony, can you hear me?
Says here this is a four-body problem with a mass at the center. And another thing to take into consideration is these are very specific. This is an assumption that they are all equal on the same plane. They're all perfectly level in space, which is very, very unlikely. You see as the triangle forms, the sphere shape, as they call it in mathematical. And that's how we visualize the difference as it moves. So singularities and collisions. Obviously, the collisions, when things crash into each other, they collide. But in mathematical terms, the collision definition is defined as RT of elements 1 through n as they approach a point R star, and when one of those two elements equal each other, as in R star J equals R star K. Obviously, when on a graph such as we saw, if they were to collide, they just phase through each other, but planets don't phase through each other. And they collide, which is also known as a singularity. And I have some theorems right here that I use in my research, where for three-body problems, all singularities are collisions. The proofs for these theorems is very, very long and rigorous, so I didn't include them in PowerPoint. But however, the reason we care about this in relation to the n-body problem is whenever celestial objects cross as defined by the existence and uniqueness theorem, we can no longer guarantee a unique solution for that celestial object, but a unique solution to the differential equation that describes where that celestial object is moving. It not only affects the body it collides with, but all others are affected by its gravitation. And loads and loads of unknown variables come about, and we can no longer solve for a coordinate point at time t at any given time. That makes it. As I played around with the research, this is what I would say is the closest thing to a general solution. There are loads of equations that are pretty similar to this one. All of them have different little tweaks and differentials that people like to throw in there, their own opinion. For mine, we're trying to find the instantaneous velocity at the body with respect to the k coordinate. J is the universal gravitational constant, mj is the object's mass, a of jk and a of ik are the coordinates of the I and j body in three-dimensional space, and the denominator I have the difference between each of these in the x, y, and z coordinate system. However, like, obviously did not solve the n-body problem, and as I played around with this equation, I noticed how as n got larger, it grew more and more inaccurate. And this is just due to the expansion of unknown variables, possibilities that can happen as more and more bodies that come about. As n just goes by one, there are 3 or 4 more new unknown variables that we cannot solve for, or we don't know how to solve for yet. The future of the n-body problem, if I was to continue my research doing this, the main thing I was trying to go for this time was an analytical with general solution. But algorithms seem to be more of the way to go. In-depth algorithms, like I said, they're not like super quantum computers. One algorithm, as far as I know, is not the best way to solve it. All of them have their pros and cons. And I just think if we were to take a step forward and solve the problem, or even get a hint towards the general solution, it would have to be through algorithms. And not only as math and physics grow, but computer science, new ways of creating the algorithms, their solutions will be done, and they would become part. We're taking a step forward in the problem. How I was able to do this research, I was given this opportunity by Perry, Pisgah Astronomical Research Institute, where I was able to be shadowed by astronomers and use them as guidance. And they have lots of various astronomical tools to use if I wanted to. The main thing being their radio telescopes. They have 2 26-meter telescopes that are gigantic, and many others that are smaller around the site. I got these through for an undergrad. You probably have your advisor emailing you all these opportunities. That's how I found out about the opportunity. And I just said, I want to work for you. I mean, these people are sending you emails to your advisors to send to you guys. If they want you, just gotta say, yeah, I want to do that. And it's pretty simple from there. I gotta pick whatever research problem I want to do. I chose the n-body problem, and they helped me out for the next 2 months in solving it.
So where was this now?
Perry, it's in North Carolina. It's in North Carolina, Pisgah Forest.
Okay.
It's in a valley in the middle of the woods. It used to be it was originally owned by NASA and then the Department of Defense, and then Perry took over.
So do you remember what your other options were? So you picked the n-body problem, but.
I could have picked any astronomical problem they said. So there's a wide variety of things I chose from, but this is the one I like. I like celestial mechanics, how things move in space. So that is it. I go into more research or in depth about all this in my paper that I wrote. It's roughly around 10 pages. If you want it, here's my email. I will email it to you. Answer any questions.
Any questions?
So if you just randomly place n bodies in space, just random coordinates, assuming there's nothing else in space affecting them, which I'm assuming is what you assume for the n body problem. Do you know if they're liable to stabilize or to in general be chaotic, or what do you normally expect to happen if you just start with random coordinates?
Your sort of randoms are most likely they're not going to be stable. If it's round 3, inevitably a 3-body problem. The third mass will get flung out of orbit, and then it will stabilize to a 2-body problem, and the third body will just go off somewhere. Maybe according to
Right, so
the system of
essentially-
bodies.
Essentially, it gangs up and imparts enough energy on the third body to give escape velocity from the system, correct?
And the way we do like our solar system, like we do as multiple 2-body problems with each planet and the sun, and we combine it all together. Obviously, it's not the exact solution to how stable our solar system is. It's actually not as stable as you think, but
Well, see, that's what I was gonna ask, actually. I mean, so obviously it's stable enough to have lasted a while, but I mean,
But long, this is mostly long term.
right, so one thing that could screw the solar system up is if some wandering star or some brown dwarf comes floating through and, you know, jerks Jupiter out or does something like that, but if we could get rid of if we could get rid of everything but the 8 planets and the sun, do you know if that's a stable system?
I do not, but I know when they were playing around with numeric solutions for Venus, they moved Venus by half a centimeter to away from the sun and close to the sun. And in 1% of the results, it ended up getting absorbed into the sun or crashing into Mercury.
Well, let's not push things too hard.
Yes.
Yeah, so related question, right? I mean, I would have imagined that the system of the sun, earth, and the moon would be a simpler case of a 3-body problem. And if you were to sort of put some constraints on what the orbits can be, can that be analytically solved?
Yes, the way they see that problem is with the Earth and Sun in relation to the moon. The moon is too small of an object or a body to have any real effect on the gravity. So they consider just the Sun and Earth a 2-body problem, or you can also do the Earth and Moon as a separate.
Yeah, the Earth and the moon should be like a single body. Right, center of, right, the Earth and moon is like a single body around its center of mass.
Because obviously in our solar system, we have things like the
And that's
asteroid
probably, I
belt.
would guess that 3-body problem is close to stable.
Yeah, like we have things like the asteroid belt in our system, and just the masses of each little asteroid is too small to be considered like a.
No, I mean, I understand the approximate solution by considering the moon and the sun as a single body, but my question was, is there an exact solution for that 3-body problem, not an approximate?
No. No exact solution for that.
Yeah, I think I read somewhere that like for the 3-body problem, classically, there were like 3 known stable solutions where they actually wrote it down. They're stable in the sense that they're periodic, right? And they repeat themselves.
Yeah.
And then like,
But
it
to
was
actually
like maybe
find
10 years ago, I think they discovered a family of like 13 stable solutions for the 3-body problem.
Okay.
And they added that, and so there were these other parameterized solutions.
in
But
the
still,
video, I showed there was a total of 15 stable body problems with a 3-body.
okay,
But actually finding those in the observable universe is just.
they're set up,
very-
right?
Yeah,
I mean,
they're set up like.
they're basically
They're
something
not
set up
even
to
in
make the math
3D
work.
space, they're in more like 2D space, so. You have to all be very
Yeah,
exactly evenly aligned.
you'd have to go to
on a plane.
Thanos to get it set up right.
Yeah.
Yeah, I get it.
For the 3-body problem, did you notice like any difference between like, just like a random dispersion of the 3 bodies or like, compared to like if they were in each other's like launch points? Did you notice?
No, I did play around with some simulations that started with 3-body. Obviously, they go up to like 20 plus bodies, and each one was pretty different. They would spin around each other. One would eventually get flung out of the orbit, and then it would stabilize as a 2-body problem.
So you ran a lot of these 3-body simulations, right?
Yeah.
And so,
That's
so
like
you
the
would
next.
say that, so how did you do that, right? So you set up, did you have that they had different masses or, and then you set up initial conditions and velocities or?
So in my paper, actually, I showed the difference between a 2-body system with an with even masses and uneven masses, and I go through the solutions for those and how they differ. And then I go through a 3rd body, a 4th body, and a 6th body, all with an equal mass at the center. And I show like how as n grows, how solving the equation changes and what new factors get to put into it.
Right, but, so when you run these simulations on computers, right?
Yeah, like I found one that was wrote in Python.
So what data did you, so did you did you have like relative mass and what initial position?
In the simulations I looked at, most of the time, it was assuming that the math are equal.
Okay, so they're all, okay, so yeah, that would simplify things. And then what, did you have like kind of so then you had their initial positions and an initial velocity or?
Their
did you just
initial
like-
positions were randomized.
Okay,
for the simulation.
how about initial velocity, or did you just let gravity control the whole thing?
They're all moving at the same speed, like the same velocity. It's just there are so many of them acting on each other that it becomes chaotic and random.
But in that situation, you say that most of the time, if you randomize the starting positions, most of the time, two of them are bullies and throw the third body out, right?
Yeah,
Okay.
obviously, if there's like 20 of them though in a group, that's probably not gonna happen. They're just. I can't tell you what's gonna happen. So.
Well, I would guess with 20, I mean, if that happens with 3, well, I would guess that what would happen is it would just evolve and time to time it would just start flinging stuff out. Is that right?
Yeah, I mean, it's very random on if something gets flung out or not, but it's highly possible, yeah. I did see one of the quantum simulations, it was so big and it just ended up forming, universes and galaxies, like spiral Milky Ways were forming. And it was all.
Okay. Okay, other questions?
I noticed that within one slide, there's a definition of collision, and I noticed also there's a term called singularity. So, could you explain what a singularity is?
Yeah, so a singularity in the n by problem occurs at a specific time t when r by j equals r star k. So when two elements equal their position in coordinate systems at a certain time, it becomes a collision, or it's the same thing.
Oh,
It's also called a singularity. I don't know why they do it, that's what they did. And then the next theorem is, yeah.
Oh, singularity. Okay.
All the proofs for these, they're in the paper, they're extremely long, they're like pages long, so I didn't put it.
Thanks.
Yes.
So you said unlike the quantum simulations, there were like spirals and galaxies and whatnot that was formed. What was like the highest order that you would have to, like the highest number of bodies?
There was one I saw with so many bodies I couldn't count. But most of the ones I saw were around like 0 or 3 to 50 bodies.
Were there any like in the higher order ones, like the ones pushed to 50, were there any like general sort of structures that would form? Like anything like spirals that would emerge or anything like that?
There would be sometimes like mini little twos would come if they got really close to a spiral, but they'd also move in accordance to everything else. And then usually a collision happened at that point. And it threw everything off. And it scattered.
Do they do the collisions by, say, two bodies get close enough to the same point? Or is it the end point?
So like saying that like two bodies are orbiting each other and they get closer and closer and closer, that could lead to a collision. That's how like non-binary stars form. They circle each other and then they combine and grow to a bigger star.
So the singularities, the collisions seem to be defined in terms of like points in the plane. So, but it seems like the probability of them being at the exact same point in the plane would be 0. So they have volumes, I'm assuming, like you give them a specific volume, because we only talk about mass and velocity, but if they're just points in the plane, I don't expect them
I
to.
see what you're saying, like it was a really
Collide.
bigger point, a smaller point.
Right.
That is a big estimate because obviously. So it's to the point where that's a very specific thing that we'd have to take into account that we're not even at that point yet to figure out volume wise. I mean, as long as the masses are close enough, it's gonna have a similar effect on the system.
I guess I'm just wondering, how does it decide in a simulation whether two things collide or not? Because with this, it looks to me like they have to be at the exact same coordinates in the
Yeah.
plane, which I would expect if they're considered to be points, that the probability of that would be 0.
Well, most of the simulations, especially like the simple ones and the intermediate ones, are done on a 2D plane. So it's not 3D, so the probability of them happening actually goes up a good bit as you take out full dimension.
Okay, But if they're points, that wouldn't make a difference whether it was 2 or 3.
Simulations generally have to discretize the plane, so it's not a
Okay.
continuous spectrum.
Okay, thank you. That makes sense.
Sure, so in one of the examples, you just had a mass in the middle, right? And that was just like a fixed point almost, right? That doesn't.
Yeah.
And
The center of mass, we're assuming that all bodies orbit around that center point,
orbit around,
in that center. of mass.
like, what would that be like? Would that kind of almost be like a black hole, or does that have any analogy?
It could be a star, it could be a really heavy planet, it could be a black hole,
Black hole, okay.
an object of great mass.
Like in the 3-body problem, when one of the bodies inevitably gets like flung out, does that center of mass still hold? Like, is that still gonna be there when one?
There's not always a center of mass in a 3-body problem. Sometimes they're orbiting around a center of mass, sometimes there's no center of mass. And say in the points where there is a center of mass,
Well,
it does get.
so I think there's always a center of mass, but what you're saying is it's dynamic.
Yeah.
It can move.
Yeah, it's like,
Yeah, well, does it become any easier if you do have this center of mass in the 3-body problem or 4-body problem, or does it not really help with finding these stable solutions?
not really. Some people like to do it to figure out one thing, but then it leads to a big con of something equally as important.
Do you know how they made those videos that you showed?
I don't know. I just found them. I thought it'd be good, like visualizations to show what is stable versus unstable.
I know what I'm doing tonight. Any other questions?
Hello, can you hear me?
Oh,
All
yeah.
right, last one. What, do you know, what's like the highest n for there being a stable solution that's maybe not just. I'm trying to think like trivial, like is it?
Let's say 4,
Four.
and it's always something trivial. It's something that we make to be perfect.
Four.
I mean, I guess you can have like 8 planets all evenly spaced out, all equal mass orbiting the exact same thing with nothing else around it.
That's what I was thinking.
You
If you
can
could have as
do
many as you
that.
want doing that.
Yeah, but.
Yeah,
That's
you
extremely
have
likely
these
to find.
mathematical solutions to this that probably don't really show up in real life.
Yeah.
There
very
are
interesting.
numeric solutions for like specific things like this, but an overall general solution that would describe any like preconditions is non-existent so far now.
Other questions? Okay, let's thank our. Thank you. Well, sign up for the math then when I nag you. And remember, next week is Thanksgiving, so everybody have a safe and wonderful Thanksgiving. And we'll be back with more talks on December 2nd. Thank you for coming out. Thank you very much. Oh, really?
If anyone wants to read the paper, just get my email right there.
Yeah.
Okay. All right. Just give my email.
You're right. Okay. Oh, hey, Brandon. Are you still there?
Hey, how are you? Yeah.